My final project was based on the FDA Round Robin Challenge. In that event, researchers were asked to simulate the flow of blood through a pipe simulating a medical device. This pipe is shown here. This was the same layout used for my own final project. Blood, being a shear-sensitive material, must not undergo high shear forces. If it does, it gets damaged. My project aimed to help researchers prevent making medical devices that damage blood by being able to simply model what are the high shear force regions in a pipe with blood flow through it. The way we did this was by beginning with an ANSYS model and the data that it provided of the wall shear stress here in the diagram provided, and then using that to generate a response surface. The response surface, being a function, can easily be optimized using optimization software such as MATLAB. I started with an ANSYS model, which I ran at a series of different operating conditions to find optimal operating conditions, and took the data from those different sets of circumstances to create the so-called experimental data from which my response surface would be based. My two variables in my design space were x1, which was the mass flow rate, and x2, which was the axial position along the pipe. And then the function that was being evaluated was the wall shear stress. So if you look here, you'll see that I have a number of plots for different mass flow rates. These are in cubic meters per second. And what is the wall shear stress along the different points from the entry to the exit of the pipe. Now, if you take all these data sets together and you imagine kind of stacking them out together in sequence from sort of an isometric view in 3D, you get a surface, and that sort of a surface is what we're going to have for our response surface, which you'll see soon. But first I'd like to point out a few characteristics of these plots here. You'll note that there's a slow progression from one set of behavior, such as with this peak here, with the lower flow rates, to a different set of behavior with no peak here and a sharp peak here and higher magnitudes with the higher flow rates. This trend continues on with higher and higher flow rates. And what we ultimately find is that we can divide this up into different regions. So for example, from here over, we could call this region 1. And then from here to here, we could call this region 2. And those regions could individually be modeled using the response surface method, which has capabilities up to quadratic. Take a look at the response surfaces that we generated. We have here a response surface for region 1 and a response surface for region 2, and each pretty well summarizes the behavior in its region. But then when you put them up next to each other and look at regions 1 and 2 together, you begin to see, and we're imagining again the behavior that we saw in the previous plots here, you can see that there's some definite discrepancies. The smooth plot that we had before isn't really reproduced by this. Specifically, you can see there's a discrete jump here from one response surface to the next. And you can see that those steep curves that you saw, many of them are muted, rounded out. So ultimately, we had a plot that correctly predicted the positions of maximum shear stress, which was what we wanted, but it incorrectly predicted the magnitudes. And although they followed the forms of the curves they were meant to model, they kind of muted those curves. And the discontinuity that existed between them meant that at a certain point here, you have two output values for one input. The goal was to create a less computationally intensive way of predicting the problem areas in medical device design and then determine the conditions where you could safely operate it. Ultimately, the results were a partial success. There was proof that the method could be viable, but it needs further improvements. Specifically, we need to use a higher order response surface to stop muting out those curves, so higher than quadratic. And we need to devise a way to eliminate this discontinuity between the two response surfaces that were created separately. Now, those two things together are going to require some custom written MATLAB code. In addition, taking more data points and dividing the plot into more regions and other more conventional measures might also improve the outcome.